Hi everyone, my name is Lydia, and this is what I wish they taught me about econometrics and introduction. Now that we have covered unbiasedness and the zero conditional mean assumption, which was at the basis of it, it's time to look at another important assumption, and that is the homoskedasticity assumption. This assumption will be very important in the future for understanding efficiency, as well as standard errors. So let's dive into what does homoskedasticity say. In its standard form, we will write it as the variance epsilon I conditional on xi equal to sigma square. Now, what that means is that the variance of the error is constant. It does not depend on the value of x. And ultimately, every observation has the same noise level. Okay. Visually, this is something that you might have seen in your lectures or in any of the textbooks or slides that you might be referring to, and you might have heard the term funnel shaped. So your data looks a little bit like this. Okay. So what is this shape really telling you? It looks almost like a cone, right? So it tells you that if you notice, for values of x that are small, so this is where the small values of x are, you have also small values of r, because this is where the small values would be. However, as your x increases in values, so in here, the variation in the values that you see for your y increases, because now look, the range for your y values goes from here to here, okay? So this is the new range. So as you can see, we are looking at sort of a cloud that spreads, and it's not the same everywhere. It's tighter and then it fans out. But why does homoskedasticity matters? First of all, homoskedasticity is not required for unbiasedness. Okay? So not required for statistical property 1. However, it will be required for two things, and that is having a clean variance formula for both the variance of the beta 1 hat and the beta 2 hat and the beta null hat. So it will be required for statistical property 2. At the same time, this assumption will also be required for the Gauss-Markov theorem, for which we will talk in another video. So for now, just keep in mind, without homoskedasticity, OLS is still unbiased. However, what changes is the debate on whether it's the most efficient linear estimator or not. How to spot heteroskedasticity? Well, apart from the graph, spotting heteroskedasticity could be done through many other kinds of tests as well. Most of the times, there will be issues with the standard errors. And the thing is, if homoskedasticity is violated as an assumption, any confidence intervals and t-tests will become unreliable. So, and this is the most important key takeaway here. If violated, we can no longer trust any of the t-values or standard errors. And why do I say and emphasize t-values or standard errors? Because when you do hypothesis testing to look at the individual significance of any of the betas that you're estimating, that means that those t-values reported to you by Stata or R, you can't take them at face value. Now, what does this assumption not tell us at the same time? Keep in mind, even if homoskedasticity is fulfilled, so you don't have to worry about it, it does not mean it doesn't mean that the errors are independent. That the errors are normally distributed. That the errors are small. Or that they have zero expectation. Okay. Or that X causes Y, most of all. Okay, so it only means constant variance. Ultimately, homoskedasticity is the assumption that will keep the variance formulas clean and gives us the OLS and its efficiency property. However, we will look into more details how exactly the homoskedasticity helps us get the formulas, especially for statistical property 2. And in the meantime, I'll let you with another video, which is should homoskedasticity be written as a conditional assumption or unconditional one, the same one we did for assumption 5. Until then, I'll see you in the next video.